So let's go back to 4.9, entitled Antiderivatives. Antiderivatives. In antiderivatives, we are trying to determine from the derivative. I'm recording. From the derivative, we are trying to determine the function. So going backwards. In other words, let's say we are given v of t. Is there any way of going backwards to find a formula for the distance? Or if I'm given a of t, if I could go back and find the velocity and then further back and find the distance. So this is the idea. So the derivative is given and we want to determine the function. Or the second derivative could be given and we're asked to determine the function. We do have two notations. And you can say, are they so important? Then you have to mention them. Yes, the answer is yes. If we are given f of x and asked to find what is called the antiderivative, so one more time before we continue, this function s of t is the antiderivative of v of t. This function is the antiderivative of a of t. This function is the antiderivative of v of t. Okay, so if we are given f of x and we are asked to find the antiderivative, then the antiderivative is denoted by uppercase f of x. Mandatory. So this is very important to understand a big theorem in chapter 5. So if we are told we are given f of x, which is x to the fourth, and we're asked to find the antiderivative, I have to use this notation to find the antiderivative. And since we're here and we mentioned this, what function prime will be this? So it will be x to the fifth power over 5, indeed. Because when I differentiate this, I bring 5 down, simplify the 5, and I get x to the fourth. Yes, I'll explain this in several times, not just one. Plus a constant c. This is called the most general antiderivative of f of x. So now let's explain how we got that. So in order for the answer to be x to the nth power, then obviously I have x to n plus first over n plus first to differentiate. So when I differentiate x to n plus first, I bring down n plus first, which will simplify with the denominator, and I subtract 1 from the power. So if I want to determine the antiderivative of x to the third, I will say x to the fourth over 4, but the most general will be this, right? So I cannot put the equal symbol, so I have to put an arrow. So when I differentiate this, I will always get x to the third. 4 comes in front, simplifies with 4. I get x to the third, and the constant prime is 0. Okay, now there is another option. What is the second option? We may be given f prime, not the notation f of x. We may be given f prime and asked to find the antiderivative. Then the notation will be f of x, lower f of x, lowercase. So
What if like you make it uppercase still? Is that okay? Or?
No. No. So if we are given f prime of x and we're asked to find the antiderivative, the notation will be f of x. If we are given f of x and we're asked to find the antiderivative, that will be uppercase f of x. Because this is specifically reserved for something in chapter 5.
And then if we were given double prime, it would just be.
If I'm given the double prime, then I will determine f prime as the antiderivative. Very good. Okay, so let's look on page 349. Hey, let's start with just a simple situation like 25 on page 348. We are given f double prime, since you mentioned that, 20x cubed minus 12x squared plus 6x. And the question is asking us to find f of x, of course. We cannot determine f of x if we don't determine f prime of x first. So, and when we're asked to find f, we're asked to find the most general f. Okay, so first we have to find f prime. 20 x to the fourth over 4 minus 12 x to the third over 3 plus 6 x squared over 2 plus a constant that I will denote by C1. How will I check this? Well, if you differentiate this, you have to get that. So when I differentiate this, I get 4, 4 goes away, and I get that. Differentiate, I get 3, 3 goes away, and I get that. 2, 2 goes away, and I get that. And when I differentiate a constant, I get 0. I have to clean it up. So f prime of x will be 5x to the fourth minus 4x to the third plus 3x squared plus C1. And now I'm ready to find f of x. And that will be 5 x to the fifth over 5 minus 4 x to the fourth over 4 plus 3 x to the third divided by 3 plus C1x and plus C2. If we differentiate this, we should get f prime. So 5, 4, 3, C1x prime is C1, C2 prime is 0. So now I clean it up. So the function is x to the fifth minus x to the fourth plus x to the third plus C1x plus C2. What does this represent? It represents the most general antiderivative of this function. Now, sometimes we are given certain conditions that will allow us to specifically determine these constants and therefore get just one function that fulfills the given conditions. Okay, so do we need another example like this, or can we look at examples in which conditions are given? We can do another one like this if you want. So what about, let's say, the third derivative, let's say 29. So we have the third derivative of t, which is cosine t. We're asked to find the function. F double prime of t is the function that we differentiate to get that. Very good. So sine t plus a constant C1. Now I need f prime. What function prime is sine t? Plus. Very good. Plus. Awesome. So now we are finding f of t.
sine c
Yes,
plus c1x squared
over 2, very good, plus,
c2x
plus.
plus c3.
Again, this is the most general antiderivative. What do I mean by that?
For those x's should be
It
t's,
should
right?
be T's, yeah.
Oh,
So the only time you have to use the capital F is if you were given f of x to start with.
correct. So, what does this mean? You can put whatever you want. Replace C1, C2, and C3 with whatever you want. So you get infinitely many functions whose third derivative is this. Not just one. Replace C1 with any number you want, C2 with any number you want, and you can continue forever. So we have a huge family of functions whose third derivative is cosine t. Okay. So now let's take a look at the following. 39. On page 349. So the second derivative equals negative 2 plus 12x minus 12x squared. We are told that f of 0 is 4 and f prime of 0 is 12. Now this is a totally different situation. We are specifically told find the function f, the antiderivative. I shouldn't say the antiderivative. I should say find the function f because we have to go through 2 steps. Find a function f that has the second derivative this, but also fulfills 2 other conditions. F of 0 is 4 and f prime of 0 is 12. Why do you think these 2 pieces of information are given? They will help us determine the constants. And that will be a unique function, just one, not a family of functions, whose derivative will be this and also fulfill the given conditions. So let's move on to f prime. Negative 2x plus 12x squared over 2 minus 12x cubed over 3 plus a constant c. Oh, we didn't get there. No. Hold on. Let's clean it up. F prime of x, negative 2x plus 6x squared minus 4x cubed plus c. Yes, and now you're correct. F prime of 0 is 12, 0, 0, 0. This means that c is 12. So then f prime of x is negative 2x plus 6x squared minus 4x cubed and plus 12. And I should present it in descending order correctly, but that's okay. I'm going to do it at the end. So now f of x will be negative 2x squared over 2 plus 6x cubed over 3 minus 4x to the fourth over 4 plus 12x plus a constant d. Or you can say C1 and C2, whatever you want. It doesn't matter, really. And now I know that f of 0 is 4. Since f of 0 is 4, that means that d equals 4. Agreed? So then f of x, finally, is negative x to the fourth plus 2x cubed minus x squared plus 12x and plus 4. Correct in descending order. And there is no other function that has that second derivative as well as fulfills the given conditions. F prime of 0 to be 12 and f of 0 to be 4. Is this okay? Okay. A particle is moving with the given data. So let's say we're given 63 on page 349. A of t equals 10 sine t plus 3 cosine t. S of 0 is 0. S of 2 pi is 12. Any questions so far? A particle is moving with a given data. Find the position of the particle. Find the position of the particle. In order to find the position, I have to find what first? The velocity. So let's find the velocity. So v of t equals, which function prime will be 10 sine t? Correct? And then plus C. I'm going to call it C1. Or C and D, doesn't matter really, whatever you want. I don't have any information about the velocity, which means I have to continue. Now I'm ready to find S of t. What do I get?
Negative 10 sine t
Correct.
plus 3 cosine t plus 3 sine
Minus.
minus 3 sine. Oh. Plus C1 X.
Very good. Plus
C1 X.
plus.
C2.
Good. I am given two pieces of information, and they will help me determine C1 and C2. So those two refer to the same function. So let's plug in 0 first. S of 0, they say it's 0. So negative 10 times 0, because sine 0 is 0, this is 0. How much is cosine 0?
1.
Times negative 3. Very good. Awesome. And this is 0. So then plus C2 equals 0, which means C2 equals 3 indeed. So I have C2. I will rewrite the function. S of t equals negative 10 sine t minus 3 cosine t plus C1t and plus 3. Now I will use the second piece of information, in which I am told that S of 2 pi is 12. So negative 10 times sine 2 pi. 2 pi is where 0 is, so, but I have to plug in 2 pi. Yes, so this is 0. How much is cosine 2 pi?
1.
Times negative 3 plus 2 pi C1 plus 3 equals 12.
So it's 2 pi divided by 12.
C1 equals 12 divided by 2 pi. That's okay. So C1 equals 6 over pi. And now we determined the distance formula. Negative 10 sine t minus 3 cosine t plus 6 over pi t plus 3. And this is the one function that complies with all given conditions. Has the given acceleration function and fulfills the given conditions. S of 0 is 0 and S of 2 pi is 12. Is this okay? And now you understand why I didn't want to do this before test 3, because you could have confused the antiderivative with a derivative. Who knows? That's why I didn't want to show this particular section before test 3.
I would have used it on the area and on extra credit probably.
You couldn't have.
Well, I know, but I probably wouldn't.
Oh, okay. Good. Okay, very good. So now let's go back to chapter 5. That was 4.9. So now I would like to go back to our lecture from last time for a moment. So I have the grades up there and I can't do that. I have to make sure that I go back out of the grade system. Sorry about that. And so this was still, I posted it here in case you're looking for it. Okay. Oh, did you find my mistake here? Is there something that you can say about it? Nobody looked. Okay. I remember I was asleep and I remember like 4 o'clock in the morning, I forgot to solve that problem. And nobody even looked at it. That does it. 5 points off on the next test. Okay, so what I was going to show you was this. Just refresh our memory before we go back to chapter 5. And if I need to go back and redo any of this, I will, promise. So we're interested in determining the area under a graph. And it can be a graph that is below the x-axis, and then I will determine the area between the graph and the x-axis, in which the area will be considered negative as possible. But for now, we are looking at a function that is above the x-axis, and we graphed the function. We had an interval on which we wanted to determine the area between the graph and the x-axis. And we looked at 2 intervals, and then we said, okay, what happens if we use the leftmost point, rightmost point, and the midpoint? So we came up with numbers for that approximation. And then we said, okay, what happens if we go from 2 subintervals to 4, and to 8, and to 16, and then 32, and then 64, etc., etc., etc.? What will happen? And we will get better and better and better approximations. But there are still approximations. So this is the base of the rectangle, or the width, and this is the height. It doesn't really matter as you increase the number of subintervals. It really doesn't matter if you use the leftmost point, the rightmost point, or the midpoint, right? Because they will be so close, and the width of the interval will be so small, smaller and smaller as n, the number of subintervals goes higher and higher. Okay, so then this is what we looked at, and we said, okay, this is the first subinterval. Imagine that the function is somewhere here above the interval. And this is the first subinterval times the height, plus the second subinterval times the height, plus the third interval, and so on and so forth. So the width of the interval, if you want to keep it the same, will be b minus a over n. And then we determined each and every point here. This is x1, which is a plus delta x. This right here is x2, which will be a plus twice delta x. This is a x3, and so on and so forth. And we created all this here. And we said, okay, so in order to determine an approximation, I would have the sum, or the sigma notation, same thing, of delta x times f of xi, where xi is from the first subinterval till the nth subinterval, right? F of x1 plus f of x2 plus f of x3 plus f of xi plus f of xn dot 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 to f of xn from I equals 0 to n. So then we wrote this, which is Riemann, called the Riemann sum. So the sum from I equals 1 through n, exactly what we just said, delta x times f of xi, which is this, if we want to expand it. But now this is still an approximation. And then I said, okay, what if we want to replace the squiggle approximation symbol by the equal symbol? Well, in that case, we have to make n approaching infinity. And that will fill in everything. Nothing will be left over. Nothing, there will be no underestimation, no overestimation. And this is exact. So the limit of the Riemann sum is the exact area. Okay. Area under a graph of a function is equal to the limit of the Riemann sum. Okay, and then I presented 2 properties. There are 3 actually, but we condensed them into 2. So the sum can be applied to the generic term and plus applied to the second generic term, or minus. If there is a constant times a generic term, we can take the constant in front, which we did. So we are limited. We cannot find the limit of the Riemann sum for anything else but three types of functions: linear, quadratic, and cubic. We don't have anything else. No other options. But we have other methods, and I'll explain the methods. Now there are four summation notations. The sum of 1, which is n, the sum of I. Unfortunately, we have to remember these. N times n plus 1 over 2. You know I don't like to do that to you. The sum of I squared, n times n plus 1 times 2n plus 1 over 6. And if you remember this one, you will. This is the squared. Okay. And then we proved one of them using mathematical induction. And then we said, okay, now we are ready. Let's choose a linear function. We chose an interval of our choice between 1 and 4. And they said, okay, now what do we want to do? We want to find the area under this graph. Okay, so we need three preps. So the delta x. Oh, I'm sorry, can you put an x in there? I'm sorry, it's delta x. I hope you copied delta x, not just delta. I'm sorry. Sorry. This is delta x. I swallowed the x. By then I was hungry, I guess. So then xi is 1 plus 3i over n, and then f of xi. And only then we put everything together, and the constant, which is delta x, goes in front. And we went through all these steps. Okay. Now I would like to do this. I would like to choose another function, either a quadratic or cubic, and show and illustrate how to determine the area, the exact area, using the limit of the Riemann sum and with the interval of your choice. Any function you want, any interval you want. Now, if you choose a cubic function and you choose the interval not from 0, it's going to take a while because we will have to cube a quantity like, I don't know, 3i over n plus 2. And we have to raise it to the third power. So that will take a while. But it's up to you. We can do that. Now, if you choose a cubic function and you choose to use an interval that starts at 0, that will be much easier. So please tell me what you want to do, or I will choose.
What do you mean by interval that starts at 0?
0, comma 2, or
Oh,
1,
gotcha.
or 1, comma 5. So if you want 0, comma 2 is one thing. If you want 1, comma 5, it's going to be different. Slightly different, more work. But that's okay. So please tell me what you would like.
Start with quadratic.
Okay, that's fine. So let's look at a quadratic function. Any quadratic function you want to come up with. It doesn't matter.
X squared minus 14x plus 7.
Okay. Very good. And the interval?
2 to 5.
2 to 5 it is. So we're asked to find the exact area under the graph of this function between 2 and 5. And we will be using the limit as n approaches infinity from the Riemann sum, which is delta x f of xi, from I equals 1 through n. Bless you. So if you remember, this is something similar to what we did before derivatives, right? We use the limit of the difference quotient before we've learned how to find derivatives using differentiation rules. Same thing here. So this is something that we do preliminary to introducing the word integrals and the concept of integrals. Just a prep, okay? Just another way. This is how they started. Okay, very good. So I need three preps. The first prep is delta x, not delta, sorry about that. The second prep will be xi. And the third prep must be f of xi. These are the three mandatory preps before you put everything together to find the limit. So can anyone give us delta x? Okay, let's write it. B minus a divided by n. This is your a, this is your b.
14 over n. 5 minus 2. Oh.
Which is?
3.
3 over n. Now xi. Remember what xi represents. And we can create that one more time. Here's xi. You know what? Let's create it one more time. I don't want to go back.
Yeah, let's do that.
So 2, 5. X1 is 2 plus delta x. X2 is 2 plus twice delta x. What will be xi?
Xi plus I delta
2 plus
I delta.
the plus I delta x. 2 plus I delta x. I have delta x, so it's 2 plus 3I over n.
So is it always going to be 2 plus delta x?
If the left point of the interval is 2, yes.
But if it was like, if we said the interval was 5 to 7, it'd be 5 plus.
Right, because this is the
Okay.
interval we picked. Correct.
So
Yes.
it's 8 plus delta x.
Exactly.
Okay.
Yes. That's what I wanted to show back there, but I don't want to waste your time.
Okay.
So now f of xi. Can anyone present that? Well, it has to be f of 2 plus 3I over n. And as you already know, I will run out of room, so I should go to the next page anyway. So 2 plus 3I over n, everything squared, minus 14, 2 plus 3I over n, and plus 7. Is this step clear? Because our function, the function we picked was x squared minus 14x plus 7. So then f of xi must be 2 plus 3I over n squared minus 14 times 2 plus 3I over n plus 7. Agreed? Yes? Perfect. So now I have to simplify this to the core before I put it in the limit, because otherwise I'll have difficulties. Now, if you find a different method and this is easier for you, please use it. But I prefer simplifying it to the core here. Maybe you can separate. The book shows a slightly different method. If you prefer that, I'm fine. If that is better for you, please use it. So here's what they do. They don't really simplify everything, but it's the same idea. It really is. 376. 376. It's the same idea. Okay, ready? So when I square binomial, how many terms do I write? Please do not say 2. Good. The first term squared plus 2 times the first times the second. 4 times 3. 12I over n plus the second term squared. 9I squared over n squared. Yes. A plus b squared. A squared plus 2ab plus b squared. So 2, that's okay. It's okay. I'd rather do it one more time. So the first term squared is 4 plus 2 times 2 is 4 times 3 is 12. 12I over n plus the second term squared, 9I squared over n squared. Better?
Yes.
Very good. Good. Now I distribute negative 14, negative 28 minus, is it 42I over n and plus 7. Is this okay? Now I have to present everything in descending order, combine like terms, simplify it as much as possible. So 9I squared comes in first. Then these two, I have positive 12I over n and negative 42I over n, which is negative 30I over n. Agreed? And then I have a 4 and a 7, which is 11. Negative 28 plus 11 is negative 17. Let me know if this is okay. Agreed? Okay, I have done all the 3 preps that I need. So now I can put everything in the limit of the Riemann sum. So let me copy it here one more time. Limit as n approaches infinity, I equals 1 through n, delta x is 3 over n, and times f of xi, which is this. That's why I simplified it. 9i squared over n squared minus 30i over n minus 17. Okay, I'm going to put this does not depend on I. So it's a constant, will go in front. So limit as n approaches infinity, 3 over n. I try to cut back on writing a little bit. I'm applying the summation to the first term, but 9 over n squared is a constant, will go outside. So the sum of I squared. Now I'm applying the summation notation to the second term, and I take 30 over n outside, and I say sum of I. And the last one is negative 17 and the sum of 1. And yes, I will write from I equals 1 to n, from I equals 1 through n. Is this understood? Is this step clear?
So basically, you need to isolate the I.
I need to isolate, because that's, first of all, I need those 4 formulas that I have to use. Secondly, there is a property of the summation notation or sigma notation that says the sum of a constant times ai is the constant times the sum, like the limit, same thing with the limit. The limit of a constant times a function is the constant times the limit, same thing. Okay, now these have to be replaced by what we know. That's the step in which we don't cross them out. I'm making a point. So this is n. This is n plus 1 divided by 2. And this is the ugly one, which is n plus 1 to n plus 1 divided by 6. This is the step in which I eliminate the sigma notation. But I have to remember those 4. If I don't remember them, I will not be able to continue from here. So the sum of 1 is n. The sum of I is n times n plus 1 over 2. And the sum of I squared is n plus 1 to n plus 1 divided by 6. Any questions so far?
How'd you get the, is it always going to be n times n plus 1 times n plus 2 plus 1?
The sum of I squared, yes.
Put over 6 every time?
Or over 6 every time.
Okay.
So if we go back to those 4, here they are. No, the other way. Here they are.
Just scroll up on that one a little bit.
Okay? So this will never change. That's why I need to emphasize them in order to be able to replace them. Ready? So then I have limit as n approaches infinity 3 divided by n. And now in brackets, 9 over n squared times n plus 1, 2n plus 1 divided by 6 minus 30 over n times n plus 1 over 2 and minus 17n. Is this okay so far? Yes? Okay. Okay. So I'm trying to see if it's worth simplifying and what is worth simplifying. So can I simplify the 2? I can, and I get 15 and the n, and there is no denominator here. But then what do I do here? So here I can only simplify by 3 and by 1n. So So I'd rather keep 2n as the least common denominator, because otherwise I have to go back and multiply if I simplify. So then I have limit as n approaches infinity, 3 over n in front, and the least common denominator will be 2n. The first one is 2n. Now here, I have to multiply these two and multiply by 3. So 2n times n is 2n squared times 3, 6n squared. 2n plus an n. Yes, 3n times 3, so plus 9n. Very good. And 1 times 1 times 3, plus 3. Now I don't simplify here. It's negative 30n squared minus 30n. But now I have to remember that this needs a 2n because it had denominator 1.
Negative 30 minus 34.
Correct. Yes, squared. Exactly. So minus 34n squared.
Could you just multiply the other by 2?
Say it again.
Could you multiply the 3 over n by 2 also?
Not yet. Yes, I can, but not yet.
You want to wait till you
Yes. Limit as n approaches infinity. The denominator now is 2n squared. And just leave it alone for a moment. So negative, this is negative 64, but plus 6. Negative 58 n squared. Perfect. Now these two, negative 21n. And now this one alone, plus 3. At this point, you can give me the answer or apply L'Hopital's rule. If you don't remember, please apply L'Hopital's rule. If you do remember, give me the answer. 3 multiplied by negative 58. So it's negative 3 times 58 divided by 2. Is that clear? Why? The degree of the top is same as the bottom. Degree 2 over degree 2. This is the horizontal asymptote, right? Or apply L'Hopital's rule. Leading coefficient over the leading coefficient. So I will simplify and get negative. Is it 87? And this is the exact area. Since it's a negative, it means that the graph between 2 and 5 is under the x-axis. I'm sorry?
What's the
Measurement unit?
Yeah.
Units squared. Whatever units squared.
Just right here.
There is no need. It's arbitrary. Yeah. Yeah. Very good. Do we need another example?
Yes.
Very good. Let's choose another function. And then we move on. Any function you want to work with. But this time we can make it a little bit easier by choosing the interval from 0, starting from 0. Let's do a cubic. Very good. So please give me any cubic function that you can think of.
3x cubed plus 2x squared plus 4.
Awesome. It is a cubic function. Great. Let's decide upon an interval. And this time, let's make it slightly easier because of the x cubed. 0 to 3. Perfect. I need 3 preps. 1, 2, and 3. I need delta x. What is delta x? Very good, which is? Very good, awesome. Then I need xi. But we start at 0 this time, so exactly. And now f of xi. 3 times 27 I cubed over n cubed plus 2
2
times
3i
9i squared over n squared and plus 4.
plus 4.
Agreed? Much easier because we started the interval at 0. So this is 81 I cubed over n cubed plus 18i squared over n squared and plus 4. Is this okay, everyone? And now we are ready to put everything in the limit of the Riemann sum. So the area equals the limit as n approaches infinity. Now I know to put 3 over n outside, and the sum from I equals 1 through n from 81 I cubed over n cubed plus 18 I squared over n squared and plus 4. See, the first problem took us 10 minutes, the second one took us 7, and now this one should take us only 5 or less. It's always the case, right? Because it's something new and the first example always takes longer. So this is limit n approaches infinity 3 over n. And I have 81 over n cubed, the sum of I cubed. Can anyone give us the next term? Yes, 18 over n squared. Very good. Sum of, that's it. And plus 4, the sum of 1 from I equals 1 through n. Awesome. Well done. So this is limit n approaches infinity 3 over n. Now this is the time in which, do not cross it out, I'm just making a point. This is the time in which I replace those. So 81 over n cubed times
N times n plus 1 over 2.
everything squared. Very good. I'm going to write it like this. N squared, n plus 1 squared over 4. Plus,
18 over n squared.
very good, n plus 1, 2n plus 1 over 6. And the last one plus 4n. Okay, there's nothing I can do to the 4. So 4n has to stay as the denominator. Here I can simplify, but I will have to multiply by 4, which is okay. So limit as n approaches infinity 3 over n, 4n. I will simplify. So the top of this is only 81, and I square this. N squared plus 2n plus 1. Here I will simplify an n, and I can also simplify by 6, but I will have to multiply by 4, which is fine. So plus 12, and I multiply these two. 2n squared plus 3n plus 1. And then this one needs a 4n. So plus 16n squared. At this point, it's okay if you just collect the square terms instead of fully simplifying everything, because that's where we're getting anyway. It's up to you. But I can't just write it. I have to show it to you. So this is limit n approaches infinity 3 whatever, we'll check it out, over 4n squared. So I have an 81n squared, and I have a 24. So 81 and 24 and a 16. So this is 40, 121. Then I have a 162, And then I have a 36, and that is 198. So plus 198n. And finally, I have 81, and then plus 12. So that's 93. And I know the answer. I hope you don't need to use L'Hopital's rule, but go ahead, it's fine. Nothing wrong with it. So what would be the answer? Exactly. 3 times 121 over 4, which would be 363 over 4. Guaranteed to be the exact area under the graph. Any questions?
Why is it 3 times 1?
Yes, because I have to distribute to all three. So after I distribute to all three, so I have the limit as n approaches infinity from 363n squared plus 3 times 198n plus 3 times 93 divided by 4n squared. So it's infinity over infinity. I can use L'Hopital's rule. So I bring 2 in front. So this is limit as n approaches infinity. 2 times 363 times n plus 3 times 198 divided by 8n. It's again infinity over infinity. I differentiate the top and I get 2 times 363 over 8. And I simplify and I get that. So 363 over 4. Or we remember from pre-calculus, same degree over same degree, as x approaches infinity, or n in this case approaches infinity, the horizontal asymptote is 363 over 4. One or the other. This is the legitimate way, right? Because now we know limits. But I'm fine if you just write the answer right away. But you can show the L'Hopital's rule, because that's part of this course. Good. Is this okay? Do we feel a little bit better about the limit of the Riemann sum? Now, we understood it, but please redo several of these problems and create other problems for yourselves with linear, quadratic, and cubic just to practice.
What's the more work when you have a cubic that doesn't start with 0?
Correct. So let me show you what's going to happen with that. So let's say we have f of x, which is x cubed minus 1. And let's say we have the interval, I don't know, 2, 5. So then delta x, the first prep is fine, is 3 over n. The second prep is fine. It's xi, which is 2 plus I delta x, 3i over n, correct? But now I get into a little bit of a problem because I have 2 plus 3i over n, which is 2 plus 3i over n cubed minus 1. So when I cube this, a plus b, we never really talk about this because we really don't ask our students to, there is really no need to get into this, but I would say. But for a plus b to the third, we do have 2 ways of determining the expansion. One is Pascal's triangle, and the other one is combinatorics. But I can give you the punchline, which is a cubed plus 3a squared b plus 3ab squared plus b cubed.
Could you just find the 0 to 5 interval and the 0 to 2 interval and just subtract it?
You could, but then you'll have to find 2 limits.
Well,
Yeah. Yeah, this is one of the properties that we're going to talk about in chapter 5.
Okay.
Yeah. So then when you write this, you have to be careful because you have this term to the third, which is 8, plus 3 times this term squared, which is 4, times this term, which is 3i over n, plus 3 times the first term times the second term squared plus the second term cubed. So do you have to use this? No, you can do it like brute force, right? Multiply square first and then multiply again. So yeah, I don't think this is really necessary once you understand the method. I would not put a problem like this with starting at 2 when it's a cubic function, because it takes too long. And everyone at this stage, you know, in this class, everyone can cube that. Nobody needs to remember this, right? You will. How will you do this? You will square first, and then multiply the squared, the 3 terms again by 2 plus 3i over n. You don't have to do this. So then you will simplify it. Do you want me to simplify it, or is it okay if I? So I'll start with this, which is 27i cubed over n cubed. Then this is 6 times, so it's 54i squared over n squared, right? This is the next. So 36, very good, I over n. And then I have an 8 minus 1, which is positive 7. So this is your f of xi. So that's the difference when the interval starts for a cubic function, when it starts anywhere else but at 0. Any questions? Any questions?